In this screencast, we continue our discussion of algebraic expressions. We discuss example 6.6, part E. In this example, we are asked to multiply the two sums, y plus 2 times y plus 3. In the last screencast, we discussed how to multiply sums. Recall that you multiply each term from the first sum by each term from the second sum. If we apply that to this expression, we take the y from the first sum and we make sure that we multiply it by both the y and the 3 from the second sum, and then we add. So I take the y times the y plus the y times the 3. Now I need to make sure I multiply the 2 by both the y and the 3. This will give me 2 times y plus 2 times 3. Now we need to simplify. Y times y is y squared. Y times 3 is 3y. 2 times y is 2y, and 2 times 3 is 6. This is our resulting expression. Now we ask, is it fully simplified? To answer this question, we have to look to see if there are any like terms that could be combined and simplified. In this particular case, there are two like terms, 3y and 2y. 3y plus 2y gives a total of 5y. So in its simplified form, this expression would be y squared plus 5y plus 6. Expressions of the form y plus a times y plus b, like you saw above, here a is 2 and b is 3. Expressions like this are very, very common in the study of algebra. So before moving on to part F, it's worth taking a moment to look at the information we've gained from working through a simplification of an expression like this. So notice when you multiply two expressions like this, you always pick up a y squared. That's because you multiply the y and the y. Notice that you're always going to be multiplying the a and the b, and you'll get a product AB. You're always going to pick up a middle term like this as well, like the 5y here. Notice the 5 came from adding the 3 and the 2, in other words, adding these two quantities together. And in general, the middle term will always have an a plus b that results from adding the a and the b together. So whenever you multiply two quantities together that have this form, you will always arrive at a result like this. Now let's move on to part F. In this case, we are asked to multiply two expressions, a difference and a sum. Recall that every difference can be written in terms of a sum by adding a negative instead. Okay, so really the problem is to multiply these two sums. We use the same idea that we used in part E. We need to make sure every term from the first sum multiplies every term from the second sum. So I'm going to make sure that this x multiplies the x squared, the 2x, and the 5. I'll do that first. So we will have x times x squared plus x times 2x plus x times 5. And now we need to make sure that the negative 1 also multiplies all three of these terms. So I take negative 1 times x squared plus negative 1 times 2x plus negative 1 times 5. Now we need to simplify. x times x squared is really just 3 factors of x multiplied together. That gives me x cubed. Using the associative property of multiplication and the commutative property of multiplication, I can reorder these factors, these 3 factors, so that I multiply the x by the x and get x squared. So the result will be 2 times x squared. X times 5 is 5x. And then we have negative 1x squared, which means we're adding a negative 1x squared or subtracting x squared. Then we're adding a negative 1 times 2x, which really means we're subtracting 2x. And then we're adding a negative 5, which is the same as subtracting 5. So this is our resulting expression. Now we have to ask, is it fully simplified? Are there any like terms? And there are. 2x squared and x squared are like. 5x and 2x are also like. So we should be able to perform some simplifications here. The x cubed stays unchanged. We have 2x squared minus x squared. That leaves us with 1x squared, or simply x squared. We have 5x minus 2x. That gives us 3x. And then we're subtracting 5. This expression is in its simplest form because there are no like terms. The next example below is the culmination of everything we've discussed involving expressions in this chapter. So let's discuss example 6.7. Express or simplify the expression below by performing all of the indicated operations, the additions, the subtractions, and the multiplications, then combine like terms in order to simplify. So let's look at part A. You can see that we're subtracting 10r from this expression. And notice in this expression, we're multiplying 3r by 2r plus 6. So there's multiplication being performed as well as addition and subtraction. Before we can subtract the 10r, we need to perform this multiplication. In order to perform this multiplication, what property do you think we'll need to use? Can you see that this product here resembles the distributive property? It's a number times a sum. Whenever you have that form, you can use the distributive property to perform the multiplication. So here, when we perform the multiplication, we will arrive at 3r times 2r plus 3r times 6, and then we're subtracting 10r. Now let's simplify. To simplify the first term here, we have to multiply, and we can use the associative and the commutative laws to multiply the 3 and the 2 together first and get 6. And then we multiply the 2 r's and we get r squared. Next we multiply 3r by 6. We can multiply the 3 and the 6 together first and get 18, and then multiply that by r. And then we subtract off the 10r. Is this expression fully simplified? The answer is no, because we have two terms that are like and can be combined. So when we combine these, we arrive at 6r squared plus 8r. Now let's look at part B. In part B, we have two expressions that are added. Each expression is the result of multiplication, however. So before we can combine like terms and simplify, we need to perform these multiplications. In order to perform the multiplications, we'll need to use the distributive property. Notice that we have differences. in here, so we will begin by replacing the subtractions with additions. So this is 5 times y plus a negative 4 plus 8 times 2y plus a negative 1. Now we perform the distributive property. We get 5 times y plus 5 times negative 4. Perform the distributive property again, gives us 8 times 2y plus 8 times negative 1. Now let's simplify. 5 times y is 5y. 5 times a negative 4 is a negative 20. So we're adding a negative 20, which is the same thing as subtracting 20. 8 times 2y is really 16y. And 8 times negative 1 is negative 8. So we're really adding a negative 8, which means we're subtracting 8. Now, is this expression fully simplified? The answer is no, because we can see that there are some like terms that can be combined. 5y and 16y can be combined, and the negative 20 and the negative 8 can also be combined. 5y plus 16y is 21y, and negative 20 minus 8 gives us a negative 28. This expression is fully simplified because there are no like terms. Now let's look at part C. In part C, we are taking one expression and subtracting off another expression. Before we can combine the like terms, we need to perform the indicated multiplications. So this problem is very similar to the problem up here. We'll need to use the distributive law to perform this multiplication, and we'll use the distributive law again to perform this multiplication. Before doing this, though, I'm going to change the two subtractions into additions. In a problem like this, where you are subtracting a complicated quantity, I highly recommend changing this subtraction into an addition symbol. So in this case, we will have 10 times 2t plus 4 plus a negative 3 times 4 plus a negative 2t. Okay, now let's use the distributive property. 10 times 2t plus 10 times 4 plus negative 3 times 4 plus negative 3 times negative 2t. Now let's simplify. 10 times 2t gives us 20t. 10 times 4 is 40, plus a negative 12 when we multiply the negative 3 times 4. Adding a negative 12 is the same as subtracting 12. And then negative 3 times a negative 2t gives us a positive 6t. And so all of these are added. This expression is not in its simplest form currently because there are like terms. The 12t and the 6t can be combined, as well as the 40 minus 12. So when we do the combining, we have 20t plus 6t for a total of 26t, and then we add to that 40 minus 12, which is 28. Okay, let's look at part D. In this case, we're asked to take this expression and subtract this expression and then add this expression. So first of all, we will need to simplify this expression. Then we need to understand how to subtract a large expression like this, and then we simplify. So let's start by simplifying the first expression. 2 times 6p. Again, using the associative property of multiplication, I can just simply multiply the 2 and the 6 together first and then multiply by the p. This would give me 12p. Now, we're subtracting this large quantity right here. It's common to make sign mistakes in cases like this, so this is another situation where I recommend turning the subtraction into addition. So I'm going to take an intermediate step, and I'm going to write minus 1 times the quantity 5p plus 2, and then plus 3. Now you may wonder why I added the 1 in that one place. Well, it's because at this next step, when I change this subtraction to addition, I'm going to take my negative and I'm going to attach it to the 1. So I have 5p plus 2 still, and then plus 3. So the subtraction, when I turned it into addition, gave rise to a negative, and the negative got attached to the 1 that I put in here. So now the negative goes wherever the 1 goes. So 12p plus. For me to simplify this, I need to use the distributive property. So I take negative 1 times 5p plus negative 1 times 2, and then I add 3. Simplify. We have 12p plus a negative 5p when I multiply the negative 1 by 5. So adding a negative 5p, that's the same as subtracting 5p. And then I'm adding a negative 2, which is the same as subtracting 2, and then adding 3. Now let's simplify. We have some like terms, 12p minus 5p, and negative 2 plus 3. 12p minus 5p gives 7p, and negative 2 plus 3 is plus 1. This expression is in its simplest form because there are no like terms. In some of the earlier examples in this screencast, you multiplied different expressions to arrive at new expressions. For example, in an earlier example, you were asked to multiply y plus 2 by y plus 3, and you arrived at y squared plus 5y plus 6. Suppose instead that you were asked to perform the reverse process. In other words, suppose that you were given an expression like this one right here, y squared plus 5y plus 6, and you were asked to write it as a product of 2 or more other expressions. So in other words, suppose instead I had given you the expression y squared plus 5y plus 6, and I told you to write it as a product, like this. This is called factoring. You've done this before. For example, if you were told to factor the number 30, you would know that you were being asked to write 30 as 2 times 3 times 5. Factoring is taking an expression, any kind of an expression. It could be an algebraic expression like this, or just a constant like 30. You're taking an expression and you're writing it as a product, like here, 2 times 3 times 5, and here as a product of 2 smaller algebraic expressions. In the next example, you're going to be asked to take algebraic expressions and write them as products. In other words, you're being asked to factor algebraic expressions. Example 6.8. Each of the following expressions can be written as a product of 2 smaller expressions. Factor each of the following. 2 results that we have already discussed will help you here, so let's review them quickly. First of all, the distributive property. The distributive property says if you have a number times a sum, you can calculate the product in this way. We can view the distributive property from the other direction, though. The distributive property also says if you have a sum of two terms where each term has a common factor of a inside it, then you can take that a and factor it out by itself, and you're left with b plus c. So notice the distributive property tells you how to take a sum and write it as a product. Another result we saw earlier. Anytime you multiply two sums that have this form, we discussed how the resulting expression would have this form. So, if you were given an expression in this form to begin with, where you have a variable squared plus some number times the variable plus another number, you would know how to factor it. Notice this is a product. So let's try out part A. If we look at the expression we're given, it does not have this kind of form. Notice there's no constant at the end. If we do look at this, however, the two terms that we have do have a common factor in them. There's a common factor of 8, namely. So we can view this expression in this form, where 8 would be the a in the expression. So I'm going to rewrite this as 8 times 3 plus 8 times a negative s. So if I use the distributive property, I should be able to rewrite this as 8 times 3 plus a negative s, which we would normally write as 8 times 3 minus s. Now let's look at B. We ask, are there any common factors in these two terms? And there are. Both terms have a factor of b, and both terms have a factor of 5 embedded in them. So we're going to view this expression in this form up here. We're going to extract the factor that's common to the two terms. So that would be the 5b. Now in the first term, if I extract 5b, I'm left with 2a. And you can check, if you multiply this back out again, you get 10ab. Plus, now I will extract the 5b from the second term, and that leaves a negative 3b. Again, if you multiply this out, you see that you get a negative 15b squared. So now we use the distributive property because we've identified what our common factor is. So we bring that out in front, 5b, and then we're left with 2a plus a negative 3b. We would normally write this as 5b times 2a minus 3b. Now let's look at part C. Notice that part C has the same form as this expression up here, because we have a variable squared, and then we have a middle term that involves one factor of the variable, and then we have a constant term. So we should be able to factor this expression into this form. In other words, for us, we should be able to factor it into two sums. The first sum will have the form x plus something. The second sum will have the form x plus something. And we need to figure out what goes in those spots. Well, think about what we know about multiplying sums. Remember how we said you take every term from the first sum and multiply it by every term in the second sum. Well, when we multiply the x by the x, that's what's giving us the x squared. Eventually, we will have to multiply this number by this number, and the result will have to be the 10. So this number times this number has to be the 10. And one last thing we know from looking at our result above, the middle term always results from adding the two numbers that are the second numbers in the sum. So if I add these two numbers, I should get 7. So, just a recap. What do we know about these two numbers? If I multiply these two numbers, they'd better give me 10. If I add these two numbers, they'd better give me 7. Can you think of two numbers that fit the description? 2 and 5 should work. So let's insert 2 and 5 in here. We can always check our work. We can see if we've done this correctly by simply multiplying out the two expressions. So let's do a check here. If we go ahead and multiply out these two expressions we've created, we make sure each term from the first sum multiplies each term from the second sum. So the x here will have to multiply out the x and the 5. So I take x times x and x times 5. Also the 2 has to multiply both the x and the 5. So I have 2 times x plus 2 times 5. Now if we did this correctly, this sum right here should simplify back to this. Well, x times x gives us the x squared. 2 times 5 gives us the 10. And what about the quantity in the middle? Well, x times 5 is 5x plus 2x. 5x plus 2x gives 7x, which is exactly what we needed. So we've done a check. When we multiply this back out, we do arrive at this. That's a good idea whenever you're factoring, to go ahead and do a check like this, multiply it out so you know you've factored correctly. Now let's look at part D. If you look at the expression in part D, notice that it fits this template up here. We have a squared variable, we have a middle term involving one factor of the variable, and then we have a final constant term. However, up here we were adding all of these quantities, whereas down here we have subtraction. So the first thing I'm going to do is change these subtractions into additions. I'll write this as u squared plus a negative 4u plus a negative 21. Now, to factor a quantity like this, we begin by writing it in this form where we have a variable plus a number times a variable plus a number. So for us, that will be u plus something times u plus something. Again, the question is what to put in these two spots. Well, let's use what we learned in the last example. We know that if we multiply these two numbers together, we should get a negative 21, and if we add these two numbers together, we should get a negative 4. Can you think of two such numbers? Well, negative 7 and 3 should work. So let's try it. Negative 7 and 3. Notice if you multiply them, you get a negative 21, and if you add them, you get a negative 4. Let's do what we did in the last example and do a check here. So I check my answer by going back and multiplying this back out. I make sure that each term in this sum multiplies each term by this sum. So the u here has to multiply both the u and the 3, so I have u times u plus u times 3. Now the negative 7 has to multiply the u and the 3. So I have plus a negative 7u plus negative 7 times 3. Now let's simplify. U times u is u squared, and then we have u times 3, that's 3u, minus 7u, which is a negative 4u, and then plus a negative 21, or minus 21. And you can see that the result is the expression we started with. So that tells us that our factorization here was correct.